Okay.
From University of Wisconsin-Madison. And he will talk to us about the fact that in machine learning, there are ways to fool a machine learning program or machine learning program to give desired results. But he will talk.
Okay, there we go. Hi, thanks for the introduction. Yep, I'm Sam. I am in my 5th year of my PhD program. And this is the most recent thing I've been doing in a slightly broader body of work that has to do with taking various techniques and formal methods and programming languages and trying to apply that to contemporary problems in machine learning. So what I first want to do is give a little bit of that broader context. So here is machine learning on one slide. And it's missing a couple of details, but the basic idea of supervised learning is that I have a whole bunch of data about the world, and I'm going to try to reason about stuff. So I'll throw all that data into this magical machine learning box, and it'll spit out this model or classifier that then allows me to take new things and say, hey, what should I do with this other thing based off of this data according to this big model that stuff came up with? And this is cool, and it's also scary when we think about how now this is used in things like self-driving cars or in the United States judicial system, where there was this kind of scandalous article a couple years ago that was pointing at this automated decision-making procedure that was used in the court of law to try to predict whether defendants were likely to commit further crimes and therefore whether or not they should be given bail. And basically, the long story short, that program was racist. And a lot of people were upset about that. And so one of the things that I've been working on over the past couple of years is, there was this automated decision-making thing. That's a program. There's this property we would like it to have, not being racist. So can we do things like formalize that as a program verification problem? Can we synthesize programs that aren't racist? And that's all I'm going to say about this. If you're interested in hearing more details of it, please find me in the break. What I will talk about in this talk is a completely separate concern that stems from the same thing about we have this automated decision making that is really in charge of pretty substantial, important decisions. And so there's an entire field of adversarial machine learning, and one of the security concerns they care about is this thing called a training set poisoning attack. And so the setup for that is my attacker capable, if they have access to the data I'm going to use to train my model, can they make some small change into that training data that then corresponds to, when I do this whole pipeline of learning a model and classifying something, some big change in that result in classification. And I'm going to focus on decision trees for a number of reasons that you can ask me about after the break. And what I'm going to do now is just go through an example of how decision tree learning works to make a classification and how this poisoning thing then can be a problem. So suppose I have this data set about mushrooms. It says, here are 4 mushrooms. It has their sizes, their colors. And I want to use machine learning to decide, hey, is some other mushroom that is large and brown edible? And so what a decision tree learning algorithm does is that it tries to break up my data set into smaller data sets based off of doing basically a 20-question style game. So it'll pick some predicate. It'll compute a score for a bunch of predicates, and it'll decide which one of these is the best splitting predicate according to this information theoretic heuristic. And so we might say that checking whether the mushrooms are brown is the best way to split up this training set. And so the mushroom I care about is brown. I'll look at the fragment of this training set that are the brown mushrooms, and I'll use this to make the decision. So in this case, all of the things in my training set fragment that I end up with are not edible, so the algorithm would spit out that with 100% confidence, the thing you care about is not edible. And this was just corresponds to a tree of depth 1 because I got to ask one question and make one split. But the algorithm behaves inductively, and you could go further, and that is too large for this example. So now suppose that my attacker has access to my training set, and they add one more element. So the thing is that because there's this weird computation that decides what predicate I select to split up my training set, adding this one element changed which predicate that was. So now the best thing according to the score that I'm completely hand-waving the computation of is not whether the mushroom is brown, but whether or not it's small. And then when I take the corresponding training set fragment, I get something that looks completely different. And now the classification has flipped from no, 100% it's not edible to, yeah, 2/3 chance it's edible. So by poisoning the training set, you could maybe poison a person. That was a joke. OK. So ideally, what we would like to do is check, like, if that can't happen, can we prove it can't happen? Because that would be a nice safety property. And so the first step is to formalize a domain-specific language where you can write this composition of learning the algorithm and performing the classification. So you get a bunch of statements that look kind of like this in this toy language that I wrote up. And the one that I want to focus on is this last one that returns the summary of the training set fragment that you end up with. If we're working with Boolean classification, so things were edible or not, that's 1 or 0. The way that we computed that 2/3 edible score was by counting how many elements had classification of 1 and dividing by the total number of elements. And you have a bunch of concrete semantics that define a computation like this. And what we want to show is that if you run the whole concrete semantics on a bunch of different training sets, the things the attacker could make, that they would all have the same classification. So I'm going to fix this very specific representation of what an attacker could do. Let's say that you have some training set T, and you also have some number n, and maybe the attacker can delete up to n elements from the training set without anybody noticing. And that gives us a whole bunch of different training sets that we would like to show all have the same classification. And while we could just naively count how many things had classification 1, we wanted to count how many things there were, we can do those same counts on the base training set, and then just do this interval division where any of those counts could be n smaller because n things could be missing. And so you can implement this, and you can take this toy data set, and when I say you can, I mean I did. This sort of toy data set is called the MNIST data set. It's a large database of handwritten digits, and I can take this one image on the left that I think probably looks like a 7, and I can say, oh man, decision tree classification, I'd really like you to tell me whether this is a 1 or 7 using all this other data you have. But not just that. What if up to 10 elements could be removed from that big data set you have? And after like some number of seconds, you get this thing that with confidence greater than 1/2, so yes, it's always a 7, no matter which of those training sets that this symbolically represents you were actually training on. And that's pretty nifty, especially when you consider that, like, combinatorically, this is an astronomical number of training sets, and so you really need to do something symbolic. And in some cases you can, and you get this nice sort of security proof. So that was a very quick explanation of all of that. If you would like more details, please ask me more questions in the break. I have a poster. Thanks.
I guess obvious question. What if the attacker adds things? What if the attacker edits things?
Right. I always get asked this question, and it makes me think I should have written my example differently. But the key insight here was that when we're doing these operations that largely involve counting, if you can remove things, the count can be n smaller, so this interval is the count minus n. But if you can add things, then similarly, the upper bound of the interval is now plus n. So certain modifications to the attack model just mean you have to slightly tweak the mathematics, but it, for the most part, works out. So that's kind of equivalent to just, so the way that I would write that down is that instead of just being the training sets that are subsets where n are missing, it's any training set where the symmetric difference between those two things is at most n. And then again, it's the same thing where you just change the interval calculations that you're doing.
One more question.
Yeah, so I'm more interested in what if the attacker directly changed the label? Like we have a picture of 7, but the attacker directly puts the label to 1. They want the model to predict this images of 7 to 1. So will your technique handle this scenario?
If I understand your question correctly, you're asking if the attacker specifically is like changing the ground truth labeling in the data set?
Yeah, so I think that's a very typical scenario in data poisoning. Like in the spam filters, people usually mark their spam as not spam so that they can make the spam filter not working. So
yeah, so it's, I mean, if it can change a large enough portion of the training set, then you're probably like helpless. That falls into this thing where you change the exactly what the abstraction is and then what the transformers are that I was describing previously, where your abstract transformers then have a different operation to them. But like this is more concerned with if the person is making the attack and they only have so much power, can you prove that it can't do anything? Whereas it sounds to me like the cases where that becomes a problem are when they have enough power that they actually can change the outcome. So.
Okay, thank.
Okay.
I don't know much about security, so the question might be a little naive, but is it reasonable to assume that we would actually know a number n of the number of poisoned examples in a data set?
So there's still a gap here between the mathematical correctness of the verification procedure and like a practical tool that people would want to use. So maybe not, but but another way, like a different way to phrase this whole thing is to imagine that you cloud sourced your data gathering, and so you had like 100 different sources, all of which gave you 20 data points or something. And now you could do this and say, well, if I had 20 fewer data points, so like one of my sources was completely unreliable, right? Now I can ask like questions like this of what is the tolerance of the algorithm with respect to having so much unreliability, right? And I think those are still interesting and good security properties, so there's definitely room to explore that. Thanks.
Okay, thanks. We'll take the other questions offline. Let's thank our speaker again. So our next speaker